This talk will focus on recent work that aims to enable efficient aerial image understanding using UAVs by exploring first small deep neural network models and second data reduction techniques in order to complement the advances and more efficient computations that are currently enabled by dedicated hardware accelerators. Computer vision has had a tremendous success over the past decades, primarily due to the increased use of deep learning, which has considerably improved the accuracy for multiple tasks like semantic segmentation, object detection, and 3D understanding. Now, these improvements have come while using larger and more complex deep neural networks and by employing thousands or even millions of images in order to learn and understand the task at hand. Now, of course, these developments have also been assisted by the affordability and availability of parallel hardware such as GPUs, which had enabled us to train these very large models. But bringing increased perception and intelligent capabilities in the embedded domain and closer where the data lives has its own set of challenges, and we just can't take these same models and put them on a lower end computing platform. Because then we need to meet some constraints that are related to low power if we're battery operated, and we don't have the same compute capabilities on these platforms. However, this is quite a desirable asset to have on-device intelligence, because it provides us with increased security and privacy, so our data do not leave our platform or device. So there's no immediate danger of someone, being the man in the middle and getting access to them. And at the same time, it avoids having to add the added latency of sending the data and getting back the decision. And of course, it can save costs because we don't have to maintain a huge cloud infrastructure to serve maybe multiple agents, but each agent has its own optimized intelligence module, which can do all this on the fly. So there's quite a lot of need to move this intelligence into embedded domain. But it's not only the computational and technical characteristics when moving from cloud to the embedded that differ. We also have differences in the application characteristics and what the intelligent agent has to do when we move to the embedded domain. So the tasks that the device has to do are limited to some tasks that are more application specific. For example, in ImageNet, which is usually where many models have been trained on, they learn to recognize thousands of classes, which in a specific application, you may not need to have that capability. You'll need maybe a handful or tens of classes. When you're in the real world, usually you need a real-time response time to understand what's going on and take a decision. That's at around 15 or 30 frames per second, roughly speaking. You need to consume less energy and be able to work under low power regimes, like in the order of a few watts or milliwatts, even for tiny applications. And usually we have a custom platform, custom form factor, and not something that is available on server side. So for many applications, the full capacity of the models that we get from ImageNet could be unnecessary, which provides us a lot of opportunities to explore what can we do with smaller deep learning models. Now, smaller models can give you a lot of advantages across their whole life cycle of their development and deployment. And one of these properties relates to the training phase. So when you have a smaller model, it will take less time to train and will require a smaller compute footprint, so it can be parallelized probably across many GPUs easier to facilitate distributed training. Another advantage of smaller models is that they can be transferred more easily on embedded hardware. Of course, this is one of the main things that make them desirable, and that's why we explore them. And this is because they are quite energy efficient if you consider that a lot of the energy is usually wasted on accessing memory, off-chip memory. So if you can keep the model on chip, then this can be a big boost for your energy performance, and this has been shown in some recent papers. So the less we're dependent on off-chip memory, the more efficient we can do things in embedded hardware. Conversely, when you have a larger model, we need more memory references to get the weights, and in result, this computes more energy. Finally, continuously updating models becomes easier when you have a smaller model. So whenever a mobile agent or a device encounters an anomaly or a situation or it might not be confident in its predictions, which may require retraining, then we need to send that data and the model to the cloud, do the training, and then we have to send back the updated model to all the devices. Now, when the model is smaller, this is much easier because and much more affordable and cheaper to do because we don't need to rely on Wi-Fi and high band connections. Now, typically we use hardware accelerators to speed up compressed and quantized versions of well-known models because the underlying operations are highly parallel, like convolution, ReLUs, and pooling. So on top of that, what if we could also try and optimize the model directly for the application rather than using something that we transfer from ImageNet? But instead of having a generic model, just trying to optimize what's the right amount of operations and what type of operations we can have in the model. So we're interested in not only optimizing the hardware, but also optimizing the convolutional neural network for the target application. Now, to demonstrate what we can benefit from using small neural networks, we'll look into UAVs and some of their applications. So UAVs are rapidly growing technology. A lot of organizations want to use UAVs to improve their operations. And in a lot of these applications, the UAV paired with a camera can be a quite powerful sensing tool. And this is one prime example where small networks need to be deployed. So we'll try and convey the benefits of using small neural networks through these applications that we're working on and concern UAVs, like in emergency response and transportation networks and search and rescue. So in these types of applications, we usually need to detect some object, whether it's a vehicle or a pedestrian, and recognize if it's something happening in the scene, like there's a danger or a fire and so on. Now, these applications rely on cameras to carry out these tasks, and where the camera feed needs to be processed in order to extract the information. But doing that on board the UAV is challenging because of the limited payloads that we can put on a UAV and the restrictions that the battery, the limited battery capacity and flight time of the UAV. So in addition to that, offloading and streaming the video to a remote computer to do the processing may not be always the case, since we may have limited connectivity, and the connectivity is not robust. So onboard processing becomes a necessary solution, and at the same time is also attractive is if we're going to optimize the UAV flight time. Now, the first use case I will talk about is patrolling and recognizing disaster events. When a disaster happens, there is a limited time to act. So we need to deploy some sort of sensing platform that can patrol the area and report any events that and map out where the danger is and what types of disasters we have in the area. So the objective here is to develop an automated platform for rapid deployment and large area coverage. So we assume here that we have some sort of automated path planning software that will tell the drone which route to follow. And then what we want to do is get the feed from the UAV camera of the area that is monitored and recognize some catastrophe like fire, flood, earthquake, or collapsed building, and georeference that based on the location of the drone. Now, since in such cases connectivity is not always guaranteed, what we want to do is develop a suitable and better platform that will have relies on a small neural network to do this recognition. The first step is to gather data that is appropriate for this task. So we first created this ADER data set, which has 5 image classes, and we can use to train a model and test its performance. Now, it's worth looking at these pictures that they're not really resembling classes that we can find on ImageNet. And moreover, these images are not center cropped like in ImageNet. So we got these out of internet, so they're right. They're not really. The first step is to gather the data for this task. So we created the aerial image dataset for emergency response, or ADER dataset, which has 5 classes that we use to train and evaluate the networks that we develop. And it's worth considering that these images do not resemble what we find on ImageNet. They're quite more noisy, and the region of interest is not center cropped most of the time. Since then, a lot of some other works have come out to that improved on the data sets and using crowdfunding. But this data set serves to create a proof of concept of small models and compare them against what is currently available. We first examine the available models. So we have the well-known ResNet models, MobileNet family of models, VGG, all these networks. And we use those to create reference models to compare against. And we use transfer learning to basically retrain them only a small portion of the networks to fine-tune for the application at hand. Now, the next step is to experiment and try and create a smaller neural network that can provide us with very similar or adequate accuracy, but could be more computationally efficient. Now, the main principles behind the design of such a small network is to find a balance between the number of parameters in the network, the downsampling rate, and the operations that are performed within the network. Now, the parameters usually impact how many convolutions we have, how many element-wise operations we need to do, and the flop demands. Now, the aggressive downsampling can improve performance because we're working with smaller tensors, but at the same time, it can harm the accuracy of the model. And finally, with regards to the operations, we have what types of convolutions and how many channels are required for the convolution. So all these are parameters that need to be explored to identify good candidate models. Now, based on these directives, we come up with the Atrous convolutional feature fusion block, which relies on depth-wise dilated convolutions to aggregate context information. So we use dilated convolutions because it allows us to increase the receptive field of a kernel without increasing the number of parameters, which in turn keeps the model small. And at the same time, we use a depth-wise convolution so that we only look at each channel individually. The intuition behind this is to take advantage of the different dilation rates, since one path may pick something up that the other does not, and the combination of these paths will result in a richer feature fusion. At the same time, an important aspect is that we employ a depth reduction at the end, at the beginning of the block, which allows us to reduce the number of channels that we apply the depth-wise convolutions later on, and this results in faster inference times. At the end of the block, we fuse things back together, either through addition or concatenation, and we expand or basically mix together the different features. Now, the block is used as a starting point to build a deep neural network that is characterized by low computational complexity and is suitable for embedded platforms. So as a first step, we have a small number of filters at the first layer that operates on the whole image. And for that, we use normal convolution just to generate some initial low-level features. Then we use a progressive reduction of the spatial resolution rather than having each layer reduce the resolution. And we end up with up to 256 channels at the end. We make use of only convolutional layers, so we don't add parameters using dense layers. Our network depth has 7 main blocks. And another thing is that we use a leaky ReLU with different mode during training and different during inference. So during training, we allow for a small fraction of the negative values to flow backwards to improve the gradient. But during inference, we set that to 0 and set for both phases, we have we clip the value at 255, which makes it easier to approximate it with 8 bits. Now, this results in a network that manages to match or at least be very close to the other well-known networks. So if we look, for example, against SqueezeNet, we have much less parameters and less than 1 megabyte of memory for the network. While with regards to the accuracy, we're really close to ResNet and VGG. And in terms of performance, we exceed the performance by more than double the frame rates of more efficient networks. Similarly, we also developed a small network for object detection called JORNet, which shares the same principles as the EmergencyNet network. And this network makes use of 3x3 filters and more affordable 1x1 convolutions. It as well reduces the feature map size by a factor of 2 progressively, and uses a small number of filters at every layer. We also updated this with the latest trends in object detection networks, and we've come up with an improved version that still is able to detect smaller objects like pedestrians. Now, we have shown that smaller networks can be beneficial, but their benefits start to diminish as the image resolution increases, especially if we need to detect smaller objects. And this is because we have two options: either to increase the receptive field of the neural network, which will mean more computations, or resize the input to the size of the network, which was trained on, and do inference there, which can distort the image or make objects even smaller. So in addition to pursuing a smaller network, it makes sense to also focus our attention to regions in the image that matter more, and appropriately selecting those regions to process next through the neural network. So in other words, we need to find ways to discard information from the image that is not beneficial. So we propose the selective tile processing approach as an efficient way of processing higher resolution images without significantly incurring computational cost, and at the same time make smaller objects detectable. So first, we separate the image, the larger image, into smaller images called tiles, which have a size equal to that of the small CNN. And we selectively process only a subset of them using what we call an attention mechanism, which is different from what you hear in the deep learning literature, and simultaneously track activity in other tiles and what we had before using what we call a memory mechanism. In this way, there's no need to resize the input image, and the object resolution is maintained. Now, this approach works as a feedback mechanism, and we'll see in detail now the two main mechanisms. So the memory mechanism basically keeps track of the detection metrics in each tile over time, and the relative position of objects which did not change significantly over a few successive frames. To keep track of what happened before and maintain a sense of how things have changed, we have a memory buffer that keeps track of the position of the bounding box with respect to the image, a detection counter for each bounding box, the latest tile that was detected in, and the confidence and class. Now, as you can see, if we have these detections and compare successive frames, if we see that the new detections do not match what we had before, then this signifies that there has been a change in that frame, and we need to somehow improve its, increase its urgency so that we can process it again through the detector. The next mechanism is the attention mechanism that its responsibility is to pick tiles to process from the whole frame based on some statistical metrics. So first we have the number of objects that are detected in the tile, the IOU that we get between the previous detections and the current detections, and the number of times over a time horizon that this particular tile has not been selected for processing, and the number of frames that have passed since that tile was selected for processing. And we put these together, normalizing from 0 to 1, and they give us a score of how important it is to process a particular tile. And based on these metrics, we set a threshold that then allows us to pick a number of tiles to process from the current frame. Now we have various forms of attention mechanisms that can be used to select a tile. Of course, the most obvious ones are to process all the tiles all the time, to only process one tile in a round-robin fashion, and then use the selective tile processing to pick only the most important ones. And we will compare these in terms of which one is more robust and gives us the best benefits of accuracy and performance. Now, using a tile mechanism means that we may end up with more than one tile to process for each input frame, which can hurt performance. The question is, can we make further improvements to the network itself so that we have this margin of processing more than one tile? And the answer is yes. So beyond making a small network, beyond reducing the data, what we also can do is apply quantization to make the model much more efficient in terms of computing. We combine a small network that we had before with quantization and tiling techniques and analyze the impact on the accuracy and the average processing time for the application of pedestrian detection. So the quantization mechanism we use uses 8-bit integers for both inputs and weights, and we use an implementation that is based on the darknet framework. Now, looking at the accuracy first, we can see that the plain GeoNet that processes the whole image achieves very high accuracy, almost 100%. Now, if we reduce that and we either quantize or not, then accuracy drops either way. So this is the impact of the resolution of the image. If we instead apply quantization without resizing the image, we get really similar accuracies than before. But if we apply some attention mechanisms plus the quantization, we remain close to the original accuracy, but in this sense, we don't have to process the whole frame all the time. And we'll see the impact that this has on the frame rate. Now, the evaluation on an embedded platform of the average processing time, we can see that starting from plain GeoNet, that resizing the image has a high impact on the average processing time. It improves by 4 times almost the performance. In all cases, quantization can lead to an increase of 30 to 100 milliseconds. Based also on the previous figure, if we use the attention mechanism, then we have also the improved accuracy, which shows us that combining tiling plus quantization plus a small model provides a good combination that can lead to a better overall performance and more efficient implementation. So in this short talk, we have seen how various techniques and approaches that relate to small deep neural network and optimization combined with data reduction and intelligent selection techniques can lead to improvements in terms of speed and accuracy. And of course, this complements the ongoing work in the area of hardware accelerators, where the parallelization can be exploited at the low level. And I think this highlights the fact that the modern applications and the applications of the next few years require a holistic approach across all layers in order to meet the demands for tiny ML applications, the very low power applications. So in conclusion, deep learning and computer vision have migrated from the infrastructure in the cloud to the edge. UAV applications are quite popular and provide a very good platform to test and evaluate techniques for edge intelligence. And some of the key techniques that people need to also explore beyond the hardware acceleration is exploring more the neural architecture search paradigm, in order to automatically lead us to small and efficient models, and also think about the application in the sense of what prior knowledge and data we can take advantage of that will lead us all together um, these main points into efficient deep vision. Thank you very much for your attention, and please visit our various repositories. And if you have any questions and comments, please don't hesitate to contact me or any of the other co-authors. Thank you.